Hello and welcome. I'm Josh Silverman, and this is Edge Ed, cutting edge education from coast to coast. Today's session, Algebra, and we're working on power rules and GCF. Let's take a look. All right, so here are my notes for power rules. You can see we've got 5 different rules right here. We're going to take it from the top. First up, multiplying powers with the same base. Now, keep this page of notes handy. We're going to be going back to this repeatedly. All right. First up, multiplying powers with the same base. So here's what we know, okay? We know that 2 to the third is 2 times 2 times 2, right? This whole thing here, this is a power. The big number on the bottom, that's the base. The little number at the top, that's the exponent, okay? So the exponent tells us how many times to multiply the base by itself. 2 to the third means 2 times itself 3 times, 2 times 2 times 2, aka 8, okay? 2 to the fifth, well, that would be 2 times 2 times 2 times 2 times 2. So what if we said, what is 2 to the third times 2 to the fifth? Well, that would be 2 times 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 2. How many 2's is that? That's 8 of them. That's 2 to the 8th. 2 to the third times 2 to the fifth, that's 2 to the 8th. What is the rule? Well, the rule is this. When we are multiplying powers with the same base, we are going to add those exponents. X to the m times x to the n equals x to the m plus n power. That is our general rule. And here is my example. 2 to the third times 2 to the fifth is 2 to the 8th. The key word here is add. When you are multiplying powers with the same base, we add the exponent. All right, next up, dividing powers with the same base. All right, before we can talk dividing powers with the same base, we got to talk about fractions. And we've got to talk about this key word, cancel. To cancel. This is what it means to cancel. 75 over 100. Oh, I know that. That's 75 cents out of a dollar. That's 3/4 of a dollar. Okay, but why is 75 over 100 the same as 3/4? We know 75 over 100 is the same as 3/4, but why? Here's why. Because 75 is 3 times 25, and 100 is 4 times 25. When you've broken up a fraction and you've got the same factor top and bottom, you can cancel those out because anything divided by itself is simply 1. So let's apply that idea to the power rules. Dividing powers with the same base. 2 to the 7th divided by 2 to the third. Well, 2 to the 7th is 2 times 2 times 2 times 2 times 2 times 2. 2 to the third is 2 times 2 times 2. This 2 cancels with that 2. This 2 cancels with that 2. This 2 cancels with that. How many 2's are remaining? 4 of them. 2 to the 7th divided by 2 to the third is 2 to the 4th. What is the rule? Well, this time it's going to be the top exponent minus the bottom exponent. When you are dividing powers with the same base, you will subtract the exponents. Subtract the exponents, keep the base the same. X to the m divided by x to the n is x to the m minus n power. My example is 2 to the 7th divided by 2 to the 3rd is 2 to the 4th. When you are dividing powers with the same base, that's when you'll subtract. Next up, raising a power to a power. Raising a power to a power. All right, so once again, we've got 2 to the 3rd. That's the same as 2 times 2 times 2. What if we said 2 to the 3rd raised to the 3rd? Well, that just means take whatever is inside those parentheses and multiply it by itself that many times. 2 to the 3rd raised to the 3rd is the same as 2 to the 3rd times 2 to the 3rd times 2 to the 3rd. Well, that's the same as 2 times 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 2. How many 2's is that? 9 of them. What's the rule? When you are raising a power to a power, that's when you multiply. 2 to the 3rd raised to the 3rd is the same as 2 to the 9th. When you are raising a power to a power, that's when you multiply those exponents. X to the m raised to the n is equal to x to the m n power, the m times n power. My example, 2 to the 3rd raised to the 3rd, that's 2 to the 9th. When you are raising a power to a power, that's when you multiply. That's when you multiply the exponents. Next up, power of a product. So this time, we're going to start off with something like this. There's not just one factor inside. There's more than one factor. 2x squared raised to the 3rd. Well, remember, what this exponent on the outside means is that we take whatever is on the inside and multiply it by itself 3 times. 2x squared raised to the 3rd is 2x squared times 2x squared times 2x squared. Now, multiplication is associative. You can multiply in any order that you want. You're going to get the same thing. So let's just group all of those 2's together. 2 times 2 times 2. Let's put all of those x squareds together. X squared, x squared, x squared. So 2 times 2 times 2, that's 2 to the 3rd. X squared times x squared times x squared, that is x squared to the 3rd. What is the rule here? The rule is when you've got an exponent on the outside of the parens, it's going to affect each of the pieces, each of the factors on the inside. It is kind of like, it is not the same as, but it is kind of like the distributive property. It's kind of like distribute. 2x squared raised to the 3rd is equal to 8x to the 6th. Power of a product. xy to the m is equal to x to the m, y to the m. My example, 2x squared raised to the third is equal to 8x to the sixth. When you have the power of a product, that's when you distribute. Notice there's quotation marks here. It's like distribute. It is not the same as the distributive property, but it's a close analog. All right, this last rule is the most challenging one. Going to have to really stretch to make sense of this one because it's very, very counterintuitive. A negative exponent. This is one of the most important rules in all of algebra. A negative exponent can never make a number negative. A negative exponent does not make things negative. 2 to the negative 2 does not equal, wait for it, does not equal negative 4. That is not true. But that's a very common misconception. So what do we do with a negative exponent? Let's take a look. All right, you remember the rule that we had a minute ago. Dividing powers by the same base. When you are dividing powers by the same base, it is simple. The top exponent minus the bottom exponent, 7 minus 3, that would be 4. Okay, great. But what if the number on bottom is bigger than the number on the top? Break it down. 2 to the third, that's like 2 times 2 times 2. 2 to the seventh, that's like 2 times 2 times 2 times 2 times 2 times 2 times 2. This 2 can cancel with that 2. This 2 can cancel with that 2, and this 2 can cancel with that 2. How many 2's are remaining? Well, there's none. There's not a single 2 left on the top. But we don't write a 0 because when you cancel using division, it does not leave behind a 0. It leaves behind a 1. What's left on the bottom? 4 2's. How could we write that? 1 over 2 to the fourth. All right, stay with me now. Now let's go back to the rule that we had a minute ago, and this will start to make some sense. The rule that we had for dividing powers with the same base is you subtract the exponents, top minus bottom. Well, if we had 2 to the third divided by 2 to the seventh, then we're doing 3 minus 7, and that gives us a negative 4. And right here, this is where we see the rule for negative exponents. As we saw just above, we know that 2 to the third divided by 2 to the seventh should end up being 1 over 2 to the fourth. We also know from our divide rule that 2 to the third divided by 2 to the seventh is 2 to the negative fourth. Therefore, 2 to the negative fourth is equal to 1 over 2 to the positive fourth. A negative exponent can never make a number negative. That's not what it does. What does it do? It flips it. A negative exponent will flip it. So here's our rule. X to the negative m is equal to 1 over x to the positive m. Here's my example. 2 to the negative fourth is equal to 1 over 2 to the positive fourth. One last little bonus rule down here, just something to keep in mind. Anything raised to the 0 power equals 1. Let's do some problems. All right, take just a couple of minutes for these. Pause the recording as you work through these problems, and then we'll check them out together. Go for it. All right, let's take a look at those. a to the second times a to the third times a to the sixth. That is the multiply rule. We're going to add 2 plus 3 plus 6. That's going to give us a to the 11th. X times x to the second times x to the seventh. Now, it might look like there's no exponent on that x, but there is. You just can't see it. It's a hidden 1. So we're really doing x to the 1 times x to the 2 times x to the 7, and 1 plus 2 plus 7 is 10. Raising a power to a power, we multiply those exponents. We wanted 10 to the 6th. The t matches with the t. T squared times t squared, that's t to the 4. The s matches with the s. S to the 5 times s to the 1, that's s to the 6. The constant matches with the constant. The coefficient matches with the coefficient. Multiply normally. 3 times 2 is 6. The variables will go with their matching variables. C to the 1 times C to the 2, that's going to be C to the 3. There's nothing to do with that D to the 4th, so it just says D to the 4th. 9a to the 3rd b squared. That little 2 is going to affect each of the factors on the inside. 9 to the 2nd, that is 81. A to the 3rd raised to the 2nd, we're going to multiply those exponents. 3 times 2 is a to the 6th, b to the 4th raised to the 2nd, that is b to the 8. 2 times 4, that is 8. A times a to the 3rd, a to the 4. B squared times b squared, b to the 4. C squared times c squared, c to the 4. 8, a to the 4, b to the 4, c to the 4. Dividing powers with the same base, subtract. 10 minus 4 is 6. Dividing by the same power, subtract. 4 minus 3 is 1. And for the coefficients, we treat them normally. What is 16 divided by 2? That's 8. W to the 4 times u to the 6 over w to the 4 times u to the 3rd. These two are exactly the same. They will cancel out completely. U to the 3rd, u to the 6 divided by u to the 3rd is u to the 3rd. Number 11. Negative exponent can never make a number negative. What does it do? It flips it. F to the negative 3 is 1 over f to the positive 3. 6x squared to the negative 1. It flips it. 1 over 6x squared. Anytime that you've got something in parentheses and a negative 1, it just literally flips that whole thing down to the bottom. All right, set A, those are the really important ones. If you want to do a little bit of a challenge, that's for set B. Square the top and square the bottom, 4r squared over 9. Cancel. 15 divided by negative 3, that's a negative 5. X to the 3rd divided by x to the 5th, that's an x to the negative 2. Y to the 5th divided by y to the 2nd, that's a y to the positive 3. Now, if you'll notice the directions that I put at the top of the page, it's going to be very similar to the directions you'll see on a typical math assignment. No negative exponents. So when you are left with a negative exponent, we are going to flip it down to the bottom, make it into a positive exponent, and we are done. Number 15, let's divide 15, 5 and 15. Those are going to cancel out and just leave a 3 right there. So the negative 3 times 3, that's a negative 9. R times R to the 2nd, that is an r to the 3rd. Last one, let's do some canceling while we're here. This 3 can cancel with that 9, it leaves behind a 3. This 2 can cancel with that 6, and it leaves behind a 3. Oh my God, and those two 3s cancel out. Let's just go across. X times x to the negative 3 is x to the negative 2. Y to the 4 times y to the 2 is y to the 6. X times nothing, x to the 5th times nothing is x to the 5th. Y times y is y squared. All right, use the divide rule. Negative 2 divided, x to the negative 2 divided by x to the 5th is negative 2 minus 5. That is going to be x to the negative 7. 6 minus 2 is 4, but flip it so that there's no negative exponents. Final answer, y to the 4 over x to the 7. All right, let's change gears a little bit. Let's talk greatest common factor. Very essential skill, a very fundamental skill in algebra. The greatest common factor, GCF, is the largest factor shared by 2 or more terms. Couple of different ways to get there. Here is the slow and sure method. Let's say that we're looking for the GCF, the greatest common factor of 18 and 30. You could just make a list of the factor pairs. 18 is 1 and 18, 2 and 9, 3 and 6. 30 is 1 and 30, 2 and 15, 3 and 10, 5 and 6. What's the biggest number that appears on both of those lists? It's going to be the 6. The GCF is 6. Now, this middle method, for a while, when I first started teaching math, this is what I taught. You break the two numbers into their prime factorization using a factor tree. 18 is 2 times 3 times 3. 30 is 2 times 3 times 5. You look at the matching factor pairs. Well, they match with a 2, they match with a 3, so the GCF was 6. That's how I used to teach it. And then one day, I'm working with this group of students, and I showed this method. And this one kid raises his hand and said, Mr. Silverman, my teacher showed us a different way. So I said, shut up, kid. No, of course, I never say that. I said, what do you say? Come on up to the board. Why don't you show us? Not really expecting anything much is going to happen. Then he showed me this. Okay, well, 18 and 30. We just do like a little upside down division bar, and we say, what's something both of those could be divided by? Both of those could be divided by 2. 18 divided by 2 is 9. 30 divided by 2 is 15. Make another little upside down division bar. What can both of those be divided by? Well, both of those can be divided by 3. 9 divided by 3 is 3. 15 divided by 3 is 5. Okay, what can both of those be divided by? Well, the only number that goes into both 3 and 5 is 1. And when I ask the question, what can they be divided by? And the answer is 1, that means you are done. So, in the last step, you're going to take these numbers on the outside, you multiply them together. That's the GCF. Needless to say, when this young man showed that problem on the board, my brain just went, what? And so I stole it. And that's the only way that I teach GCF. Now, we call this the ladder method. There's another name for it, but I call it the ladder method. I didn't invent this, but man, I sure did steal it. Let's do a couple. 40 and 88. All right, ladder method. What can both of those be divided by? Don't think too hard. Keep it simple. They're both even numbers. Let's divide by 2. 40 divided by 2, that's 20. 88 divided by 2, that's 44. Keep going. What can both of those be divided by? Let's do 2 again. 20 divided by 2, that's 10. 44 divided by 2, that's 22. What can both of those be divided by? 2 again. 10 divided by 2 is 5. 22 divided by 2 is 11. What is the only number that you can divide both 5 and 11 by? 1. And when the answer is 1, that means you are done. Stop right there. Take a look at everything that's on the outside. Multiply those together. 2 times 2 times 2 is 8. All right, number 2. 120, 150. Special rule here. Whenever you are factoring and both numbers end in a 0, there's only one thing that you should be picking for your first number that goes on the outside, because anything that ends in a 0 could be divided by 10. And it's the easiest thing in the world to divide by 10. You just take the 0 off. 120 divided by 10 is 12. 150 divided by 10 is 15. What can both of those be divided by? Yeah, 3. 12 divided by 3 is 4. 15 divided by 3 is 5. And what can both of those be divided by? 1. We are done. Multiply them together. GCF is 30. Let's do some problems. Try page 4 for me. All right, the first couple are going to look exactly like what we just did. 90, 480. What can we divide them by? How about a 10? That's a 9 and a 48. What can we divide those by? How about a 3? That's a 3 and a 16. What can we divide those by? Only 1. We are done. And the GCF is equal to 30. 24 and 336. What can we divide those by? How about 2? 336. You can do that using mental math. Half of 36 is 18. Half of 300 is 150. 300 and 150, 168. What can we divide those by? They're still both even. Let's do 2 again. 168 divided by 2. This is even easier for mental math. What is the 8 divided by 2? That's a 4. What is the 16 divided by 2? That's an 8. But of course, it's in the tens place, so it's an 84. What can those be divided by? Let's do 2 again. That would be a 3. That would be a 42. And what can those be divided by? By 3. 3 divided by 3 is 1. 42 divided by 3 is 14. Obviously, the only thing you can divide 1 by is 1. That means we are done. Take all of these, multiply them together. 2 times 2 times 2 is 8. 8 times 3 is 24. So yes, if one of the numbers is 24, the GCF could actually be 24. Okay, now we get into a slightly higher level. Definitely a higher level. Now we're going to be doing GCF with variable expressions. Start off exactly the same way. Just worry about those numbers in front. 18 and 54. What can both of those be divided by? They can both be divided by 2. 9 and 27. You know what? Both of those could be divided by 9. Let's just cut to the chase. Take out a 9. What does that leave behind? ABC. Take out a 9. What does that leave behind? 3AB squared. Now, what can both of those be divided by? Well, even though there's no number in front of this, there is a number. You just can't see it. It's another one of those hidden ones. And the only thing that goes into both 1 and 3 is 1. But 1 is not the only thing that both of those terms can be divided by, because both of those have an A in them. Let's divide them both by A. If we divide ABC by A, that's going to give us BC. If we divide 3AB squared by A, that's going to give us 3B squared. And what can both of those be divided by? They can both be divided by B. Now, if you do BC divided by B, that's going to leave just a C behind. Take a look at this over here, though, okay? 3B squared divided by B does not equal 3 squared. It doesn't work that the letters cancel out and you leave the squared behind. Here's how I want you to picture it. 3B squared is the same as 3 times b times b. And if we're dividing that by b, these cancel out. What is left behind? 3b to the first. Now there's really nothing else that we can divide them both by. Let's multiply it all together. 2 times 9 times a times b, that's going to be 18ab. There's your GCF. Take out the 2. Take out a 2. Take out an x. Take out a y. Take out another y. That's it. That's as far as we go. Oops, lost focus there. That's as far as we go. The only thing left that can divide into both of those terms is a 1. What is the GCF? 2 times 2 times x times y times y. That is going to be 4xy squared. That would be our GCF. There we go. 18m squared n squared, 66m to the third. Now, I know that these could both be divided by 2. They could also both be divided by 3. How about we divide by 6? That's going to leave a 3m squared, n squared, 11m cubed. What can both of these be divided by? These can both be divided by m. They can also both be divided by m squared. Let's cut to the chase. M squared, that's going to leave behind 3n squared, 11m. That's as far as we can go. No more common factors. What's the GCF? 6m squared. Last one on this page. Both of those could be divided by 36. 72 is 36 times 2. You can see I'm cutting a little bit ahead on some of these now that we've got the hang of it. What could they both be divided by? They could both be divided by a single r. They could both be divided by s squared. Let's do it all in one go. rs squared. What is 2r squared divided by rs squared? That's going to leave us with a 2 and an r. What is rs cubed divided by rs squared? Just leaving behind a single s. We cannot go any further. Here is your GCF, 36rs squared. All right, one more page to wrap us up here. Now, instead of saying find the GCF, the directions say factor. And that's usually what you're going to encounter on an algebra level math problem, is they're going to tell you factor this expression. Sometimes they'll say factor completely. So here's how that works. Imagine that we're doing the GCF just like we did before. What could we divide both by? A 4. 12a divided by 4, that's a 3a. 4 divided by 4, not nothing, not nothing. It's a 1. And just keep that little sign right there, okay? Now, the difference is, unlike before, now our job is to end up with a factored form, not just the GCF, but a factored form of the original expression. And so the way that works is whatever is down here, that's what goes inside of the parentheses. Whatever is out here, that's what goes to the outside. Final answer, 4 times 3a minus 1. Go ahead, take a minute, try the rest of this page. All right. What can we divide both of those by? We can divide both of those by an x. What's left behind? An x, a minus 2, final form, x times x minus 2. What can we divide both of those? All of those by is a 3. What else can we divide all of those by is an a. 3a, that's what goes on the outside. What do we get if we divide this piece by 3a? What will be left behind is a 4 and a b. What will we get if we divide this piece by 3a? What will be left behind is a minus 2 and a c. And what will be left if we divide this by a 3a? Just a minus d. 3a times the quantity, 4b minus 2c minus d. Number 12, factor out of 4a. What's left behind? X plus 2y minus 3z. Number 13, we could factor out a 2. We could factor out an x. What's left behind? 5x squared plus 4x minus not nothing. What is 2x divided by 2x? 1. So it's minus a 1. 2 times the quantity, 5x squared plus 4x minus 1. Number 14. We could divide by a 4. We could divide by an x. We could divide by a y. 4xy. That's what's going to go on the outside. You can see I've picked up the pace here and eliminated some of those ladder method steps. You could still use the ladder method here, but this is the faster version. Mental math only. What is 8x squared y divided by 4xy? Well, that's going to leave us with a 2 and an x. What is 4xy divided by 4xy? A 1. And what is 12xy cubed divided by 4xy? That is going to be a y squared. Number 15. Definitely can divide by 5. Definitely can divide by at least 1a. And when I want to know what number goes on the outside, I look at the smallest exponent. The smallest exponent is 2, so the most we could take out is 2a's, an a squared. The smallest for the b is 1, so the most we could take out is a b. 20a to the 5th b divided by 5a squared b is going to be 4a to the 3rd. 15a to the 3rd b to the 4th divided by 5a squared b is going to be a 3a b to the 3rd. 10a squared b to the 6th divided by 5a squared b is going to be a 2. The a's cancel, and we want b to the 5th. Last one, number 16 here. This is where you would factor out a negative. If the leading coefficient is negative, that would be the only time that you'd want the thing on the outside to be a negative. So 12, 8, and 16, all of those could be divided by 4. So we're going to divide by a 4, but we're going to make it a negative 4. They can also all be divided by an a, so it's a negative 4a. Negative 12a cubed divided by negative 4a is positive 3a squared. Positive 8a squared b divided by negative 4a is negative 2ab. And negative 16ab to the 3rd divided by negative 4a is positive 4b to the 3rd. One little bonus for you down here. This trick is going to happen pretty often if you're dealing with a rational expression. I call these algebraic fractions. This is when you've got a fraction with letters in it. And anytime that you see an expression like this, Anytime that you're doing anything with rational expressions, factor first. So take the GCF of the top, 36x to the fourth y plus 60x to the third y. What can we divide them both by? How about a 6? How about an x cubed? And how about a y? So if we divided this by that, it's going to give us 6x. If we divided this by that, it's going to give us 10. Oh, we can do one more round. Let's divide by a 2. That's going to give us a 3x plus 5. What is on the outside is all of that matched together. So when we simplify this fraction, it first gets factored into 12x cubed y times the quantity 3x plus 5. And then what's on the bottom? 12x cubed y. Well, would you look at that? This entire expression cancels with this entire expression. And as often happens with these types of problems, you're left with something that is much, much simpler. When we simplify this whole complicated expression, it turns into just 3x plus 5. That's what I've got. Thanks so much, and I'll see you next time. Bye-bye.